Okay, for integration by parts to be of any use to us, we have to have it work for more complex examples than that one. So let's try a new one that's just a bit more complicated. Let's make it, well, I'm always getting the wrong pin out. Here's my pin, and there's a color. Let's see if that's going to work. Let's integrate the function x squared e to the x dx. Well, we've got in our mind this equation, or maybe on the note card, and so we set up our table. That's the first thing we have to do. We say u is equal to v is equal to du is equal to something, and dv is equal to something. And we're looking for a u and a dv, this component here, to be here. So we've got to partition up. Either u is going to be x squared or u is going to be e to the x. In the first example, I said what we want to do is find something where its derivative, du, is going to be simpler. Well, if I pick u to be e to the x, its derivative is e to the x. Nothing got simpler. So I'm not going to pick that. If I pick x squared here, then its derivative is 2x. Now I'm going to argue, and I'll convince you of this in a minute, that 2x is actually simpler than x squared, and I'll show you why in a minute. But that means that what's left must be dv, and that's going to be e to the x. But that follows a nice pattern that we can always integrate and differentiate e to the x. And to find v, we just take the antiderivative of dv, and that's just going to be e to the x. So we're now ready to plug into our equation, and we get that this integral is equal to u times v, which is just x squared e to the x, times, minus the integral of v e to the x times 2x, but let me just pull the 2 out right now. No reason to have that in there. It's just a constant times x dx. I should put my little dx down here too, shouldn't I? Well, wait a minute. E to the x times x, I don't know how to integrate that. So we're still stuck. So what to do? Well, what if we take this little part of this equation out for a minute and consider it by itself? Just integrate x e to the x. I'll just write it a little differently, different order. And now we recognize, well, wait a minute, couldn't I do this integration by parts? Just like the chain rule can be applied more than once, what if I try to integrate by parts more than once? I set up my table. That's the first thing I always do. U is equal to something, du is going to be equal to something, v is equal, dv, and now what we've got to do is partition up this equation into u and dv in some way that's going to be useful. And obviously, since I want to make the derivative of u to be simpler, we're going to put x here. Oh, mislicked. And so the derivative of u, the derivative of x, is just dx. And dv is e to the x. And we don't mind v being e to the x because we can always integrate that. So we plug into our equation here, and we find that this is going to be equal to x e to the x minus the integral of e to the x dx. But this term here is just going to be equal to e to the x plus c. So we can rewrite this whole thing. We put this term minus this term. You see what I'm doing here? And we'll put it back up in here and say our grand total answer is integral of x squared e to the x dx is equal to the first bit right here, x squared e to the x minus 2, and now we've got to bring this part up. So we'll put a big old bracket here. X e to the x minus e to the x plus c. Now we distribute our 2 through, or minus 2 I guess would be easier to do, and we get x squared e to the x minus 2x e to the x minus 2e to the x plus, it doesn't really matter what we do to the c, it can be anything, so we'll just leave that as c, and that's our answer. So the trick here was we picked a u that simplified, and then by applying integration by parts twice, it simplified to a form where we could actually integrate this term, and then we could plug back in and get our answer.